And here we are. It's the physics video lecture, Physics 190 video lecture 10. So we're coming towards the end of our course here, and a couple of major applications I still want to do and bring things full circle, as it were. So what we have remaining, in fact, let's go ahead and write this. We have residue theorem, and some interesting integrals. But we also have a physical application. And that's what we're going to talk about first. So we'll actually use the residue theorem in our physical application. But there are some interesting integrals I'll bring along as well next time. And that'll probably be it. But the physical application is the damped driven oscillator. This has the advantage of being an object that we've studied in great depth, so we should be able to recognize everything that's going on when we talk about it in terms of the complex plane. Damped driven harmonic oscillator. So that's our goal. As far as the residue theorem goes, I'll just go ahead and formulate it. We're going to use it. So we have, for some function with some singularities, there is a contour. We have the integral f of z dz on that closed contour was equal to the 2 pi I times the sum of all the residues. So residue of f of z, sum over all the z sub I, I'll just call them. And we had a couple of formulas telling us how to get these residues. And the most basic version is something that we already had with Cauchy's integral formula, but we were able to do a couple of theorems that extend the range of this calculation. Good, so that we had that, and we're going to use this. And next I'll remind us of what got us into this subject in the first place. We were doing the Fourier integrals, and the Fourier transform of Fourier integrals / Fourier transform of e to the minus ax squared. And what we had found was that this was an integral from minus infinity to plus infinity. So we say plus r and negative r. And we weren't doing the entire half circle at that time, but we did have, let me put it this way, limits. So this was in the very first lecture that we did here, as well as what our work last semester. Limits of integration from minus r plus I, some constant k, to positive r plus I, some constant times k. Look up what the constant was. Point is, we were here and here. Make that look more symmetric. And apparently, our path of integration would be down to the real axis because we were calculating a real integral, and then back up to here. So we just did the integral and ignored these two branches here. and it worked out. Now with what we've done, you should be able to convince yourself that that was completely legitimate. If you take any constant, any value of k, you would then just be able to find an r that's much bigger than that k, and this integral here would have contributions at the ends there, these branches we'll call them, these contributions, that would be negligible and would vanish in the limit as r goes to infinity. Limit r goes to infinity. So that's just to remind you what we set out to do, and that's definitely covered. In fact, go ahead and look at it again and convince yourself that those will certainly go away. Good. So now we're in the Fourier integral realm, and I'll go ahead and write those down. And this was the end of the last lecture. I'm just going to remind us what we have here. So we have the ability to express a function of x, and this was taken as a limit from the Fourier series. Integral from minus infinity to plus infinity, f hat of k e to the I k x dx. And then the Fourier transform, which is this f hat of k, is given by this reciprocal formula, 1 over 2 pi minus infinity to plus infinity, f of x e to the minus ikx dx. So first thing here, this is dk, right? We're integrating over k, and x appears right here, and over here we're integrating over x, and the argument k appears up there as well. Okay, so this was just math, but if we're going to look at this in terms of physics, our quantities have dimensions. So if x is a length, I'll just write length like this. If x is a length, then k, of course, has to be an inverse length. K length to the minus 1. So what we're going to do now is we're going to talk about the damped driven oscillator. We have to translate this to functions of t. Okay. Anything else? Oh yeah, an important point in both of these here. I'll just put this as a note. F of x and f, so f of x appears here, f hat of k appears here. They both have to vanish sufficiently rapidly as you go out to infinity. Okay. So f of x and f hat of k go to 0 as x goes to infinity, k magnitude go to infinity, respectively. Okay. And they have to go sufficiently fast so that these integrals converge. So that the integrals will converge. Okay, so how do we translate this into our problem? We'll use this board. So to translate this into time, we want, because we're doing the oscillator, we want, and in fact we want x of t, okay, for the oscillator. So we have to have formulas like this. X of t is equal to the integral x hat of k e to the I omega t d omega. Okay. And I'll go ahead and put the integration boundaries in as well. And t has dimensions of time, omega has dimensions of inverse time, the product is dimensionless. But otherwise, we've just translated this formula here. So our x hat of omega, 1 over 2 pi, x of t e to the minus I omega t dt. Okay. So that's a direct translation of these. Anything else to say? Good, let's send that up. So there's our formalism, and what we're going to do is make use of the full complex plane and the residue theorem to solve this problem. And what's going to be interesting is that the poles here take on a very clear physical significance. Okay. And we'll see that when we get there. Okay, so let's talk a bit about the damped driven oscillator. We'll write down the differential equation. So, damped driven oscillations. Been a while since we did that, but we spent a lot of time there. Remember, we had, in fact, let's be thorough. We had Newton's law, first of all. So Newton's law with minus kx, that was the restoring force, and then we had minus b times x dot, that was the velocity dependent friction force, and then we could have a driving force f of t as well. So that was just Newton's law for a mass that can move in one dimension. So mass times acceleration, restoring force, add some friction, velocity dependent friction, driving force. And what we did was we turned it into second derivative plus 2 gamma first derivative plus omega naught squared x equals driving force over m. And then we had just 2 gamma is this b divided by m. Omega naught squared is k divided by m. And we then talked about the driving force. Okay. And the driving force was going to be sinusoidal, so we have f of t is f naught times the cosine. And we're going to use a different omega because all of our omegas have been taken up already. So we're going to take the driving frequency, omega t. And in fact, we took an e to the I omega t and then did some interesting stuff with taking the real part. This time we're actually just going to use the real function cosine of omega t. And the result of this is x of t is equal to x of the homogeneous equation plus x of the inhomogeneous equation. So t here. The homogeneous equation being where f of t is equal to 0, and that, of course, is a transient. So this equals something that is something proportional to e to the minus gamma t, so that's the transient part. Okay. And then we also get something where there's an amplitude cosine omega t plus some phase difference. Yeah, so this is, I've left out the oscillatory part of the transient. Okay, there's an oscillatory part that goes away as t goes to infinity, and you're just left with this. And as you remember, that this amplitude had all the information, had quite a bit of information. So this amplitude depended on the force, the mass, the driving frequency, omega naught, right? It depended on everything. And there were a lot of interesting cases, and we had resonance and so forth. So what we're going to do is try to get all of that out with this approach up here. Good. Okay. So you have that in your notes, what we did at that time. Transient that decays, you're left with this driven part. And depending upon what's going on with the driving frequency, this amplitude could even diverge, right, in certain limits. So this amplitude was a pretty rich object. Okay, yeah, so I just wanted to set this up and remind you, wondering what else there is to remind us of. We're going to use this complex formalism to tease out the entire answer here. And I think, yes, everything's up there. Okay. So once again, we're going to have x of t be equal to integral x hat of omega e to the pi omega t d omega. And since there's our differential equation, and there's our driving force, we're also going to have to deal with f of t equals integral f hat of omega e to the I omega t d omega, where that f hat of omega equal to 1 over 2 pi f of t e to the minus I omega t dt. Okay. Now here's our strategy. We're going to first, because x of t is the unknown function, so we have to do something clever there, but the driving force function is given, and so we're first going to work on that. So we'll find its Fourier transform. And by the way, all these, if I don't put the boundaries of integration down, they're just the entire real axis, minus infinity to plus infinity. So, okay, so there's our program. We're going to take this into here, but first we're going to find f hat of omega. So first, we find f hat of omega, because that's a given, a known function. And let's go ahead and write that down. Hat of omega equals 1 over 2 pi. In fact, f hat omega for f of t equals f naught cos omega t. And I'm going to stipulate something here, t greater than equal to 0. So our problem that we're going to solve is that we turn on the driving force at t equals 0, and it's a sinusoidal driving force of this type. So our solution actually would have the transient growth and decay of the motion, right? Because if it starts at rest, t greater than 0, yeah. If it starts at rest, then it will first be driven to some amplitude, and then transient will go away. Okay, so that's in there, t greater than equal to 0. And for that reason, our boundary of integration, first let's write this down, cosine omega t e to the minus I omega t dt is defined for t positive, so from 0 to infinity. Now we actually run into a problem, because this integral, or this integrand, does not vanish. Okay. This does not go to 0 as, what are we integrating over? T goes to infinity. Okay, it just oscillates. So that's a problem that has to be dealt with. And what we're going to do is multiply this by what's called a converging factor, something that'll make it vanish at infinity. And here, I'll go ahead and write that down. I'm not going to give it a new name, but since it's right underneath here, I'll just write here, instead we use a converging factor, and that'll be defined in what I write down next. So what we get is f hat of omega equals 1 over 2 pi, 0 to infinity, f naught cos omega t. Now the converging factor we multiply by e to the minus alpha t. Alpha is positive, e to the minus I omega t dt. So this, of course, is going to converge just fine. And what we do is the entire calculation with e to the minus alpha t, and at the end we can take the limit as alpha goes to 0. In fact, we get 2 for the price of 1, so to speak, because this is a damped driving force, and that would, that's a solution that's interesting in its own right. But when we're done, so at the end we'll go ahead and end of the calculation, let alpha go to 0. And we'll see this throughout the rest of the calculation, is a really instructive thing. So this idea of a converging factor, very useful. And that is right there. Okay. Good, so now we have our work cut out for us. We just have to do this integration, not so bad though. And let's see what happens here. Okay, so our integral looks like this now. We have f hat of omega 1 over integral 0 to infinity. We've got an f0 here. Now, the cosine omega t, we can write as 1/2 e to the I omega t plus e to the minus I omega t. And then we have e to the minus alpha t, e to the minus I, lowercase omega t. So we can get all of these under, okay, so we'll have f naught over 2, 0 to infinity. So we have e to the I omega minus I alpha. Omega, no, plus I alpha, because I times I will give us a minus sign there. And then minus omega I, that's omega t. And for the second one, we have e to the minus I, and what do we have? Capital omega, and then minus I alpha this time, because minus I times minus I is minus 1, minus I alpha t, and then plus omega t. So we do that integral, dt. So we go 1 over 2 pi, f naught over 2. And now you see we're going to have 1 over I times omega plus I alpha minus omega. Times this function, evaluated from 0 to infinity. At infinity, because of the converging factor, I times I is minus 1 minus alpha t. Because the converging factor, that just vanishes, so we just have the lower bound, and the lower bound will be, it'll be minus e to the 0, so that just gives us minus 1 right there. Then we have for this second integral, 1 over minus I omega minus I alpha plus omega, okay? And again, we evaluate t equals infinity, vanishes, at t equals 0, we get a 1, so we just have a minus sign here, so I can call that plus I. Now I want to do one more thing with this expression, that is to put it into a more standard form, although it's good as it stands, but I could put it into a more standard form and then rationalize. So let's see, we would have 1 over 2 pi f naught divided by 2. I'll even pull out the 1 over I. And then for my numerator, let's just go ahead and write it out. I'll have minus omega plus I alpha plus omega, cross multiplying, plus omega plus I alpha minus omega. Minus omega plus I alpha plus omega. Minus omega, there we go. Numerator and denominator, we're just going to multiply these together. But what we're going to do is write omega minus something each time. So here we'll pull out a minus sign, and we'll have, from this, here we'll have omega minus I alpha plus omega times, over here, omega minus I alpha minus omega. Okay, that's pretty good. So these cancel here. and we have 2I alpha minus 2 omega, and we get rid of that minus sign there. So when all is said and done, and I can just put this right here, we have f hat of omega equals f naught over 2 pi I, because we're going to get rid of a 2 from the numerator there, and we'll get rid of that minus sign as well by writing omega minus I alpha divided by omega minus I alpha plus omega I alpha minus omega. Okay, so this let's showcase and study a bit. Good enough. Okay, so let's send another. So from our program, we've now found this f hat of omega. And I'll show you what the form of it is in a moment. It's not as complicated as it looks. So we found f hat of omega, and therefore f of t is available to us. We would take this f hat of omega times e to the I omega t d omega. Okay? Something we could do. Okay, so first let's say a couple more words about this. Because we have all these constants here, this looks a little more complicated than it really is. So I'm just going to put a note about f hat of omega. F hat of omega has the form it's really f hat of omega equals some constant times, I won't change the name there, omega minus I alpha. Okay, some constant omega minus I alpha, but the denominator omega minus omega 1, omega minus omega 2. Okay. So you want to simplify that a bit, because we've been doing these problems. Think of z, right? We were talking f of z, z minus z sub 0. Okay. So you can see these are just simple poles at omega 1 and omega 2. If you're in the complex plane, you've got these two locations. And I'll even draw that. Where are those poles? So here's our complex plane. This is our omega axis instead of z. So we have one at I alpha plus omega and one at I alpha minus omega. So this would be minus omega, this would be positive omega, this would be I alpha. So yeah, we have poles right here and right there. And because we're doing everything, it has a natural, more complicated form, but when we were just doing the math, this is the kind of object we were looking at. Yeah. Good. So far, so good. Let's see how we're doing time-wise here. Oh, man. We've got nothing but time. Okay, so now let's set our problem up. So we have, that's the best way to do it, we have our differential equation equals f of t over m, and we have x of t equals integral x hat of omega e to the I omega t d omega. That's eventually the integral we're going to have to do, but we don't have x hat of omega yet. And we have f of t over m equals f hat of omega over m e to the, I can fit that in here, I omega t d omega. Okay, so we have those two ingredients, and we just found the f hat of omega. So we're actually well on our way. What we do next is differentiate through this thing. So if this is x of t and this is all well behaved, we're assuming minus infinity to plus infinity, well behaved because of our damping factor, then we can just differentiate under the integral, and I will get integral x hat of omega. This is what we did, in a sense, the original time when we did the exponential ansatz, but now we have this Fourier ansatz. So let's take two derivatives. We get minus omega squared. Then we take 2 gamma x dot, so we have plus 2 gamma I omega, right? We're just differentiating this exponential complex exponential each time, and then we have plus omega naught squared. Okay, close parentheses, e to the I omega t d omega equals this f of t. I have that up on the board so I can erase this now. So equals f hat of omega over m, etc. So this integral here is integral, but we're going to go ahead and write it in, f hat of omega, so we'll have f naught over 2 pi I times m now, times omega minus I alpha, omega minus I alpha, plus omega, omega minus I alpha minus omega. E to the I omega t d omega. Okay, minus infinity to plus infinity, there's our integrals. And there's our equal sign. So what makes these integrals equal? If the integrands are equal, the integral will surely be equal as well. Okay, so that's what we're going to make the claim of. The integrands are equal, so what is the integrand? X hat of omega times this here, leaving off the e to the I omega t, right? Equal to this right there. So setting those equal, okay. If those are equal, then we can solve for x hat of omega. Solve for x hat of omega. And that's what we'll do next. And then I'll dump it all in your lap. Okay, we'll see here. For you guys to work on. Oh, actually, I'm willing to take this one as far as we have to, because we want to really understand everything that happened here. Okay, so yeah, that's our strategy. We set these equal. That allows us to get an expression for this x hat of omega, and then we're going to go back into our integral and do it. let's, there's one more thing we have to do though. May as well do it now. We're going to factorize this polynomial as well. But we know the roots of that thing. We know them already, but we could just do, it's just a quadratic formula. I'm going to go ahead and pull out a minus sign, so we've got omega squared minus 2 gamma I omega minus omega naught squared. Okay. And we want to find the root, so we can write that down. Factorized equals minus just quadratic formula. So omega equals 1/2 2 gamma I plus minus root minus 4ac 4 omega naught squared minus 4 gamma squared. So that's I gamma plus minus omega naught squared minus gamma squared. Okay, those are the two roots. And if I didn't say it before, I'm saying it now. It's the underdamped case that we're looking at. So omega naught squared is greater than gamma squared. We're looking at the underdamped case. So the point is, we can write this as minus omega minus I plus I gamma plus root omega naught squared minus gamma squared times omega minus I gamma minus root minus gamma squared. Same thing is going to hold for this factorization that I wrote about the other one. We now have x at omega equals f naught over 2 pi I times m. That's over there. I'm going to have omega minus I alpha. And now I'm dividing by these 4 roots. In fact, I've got a minus sign, so I'll just put a minus 1 here. Yeah. So, omega, I'm going to write these 2 down first. Omega minus I alpha plus omega minus omega. And then these 2 right here. Omega minus gamma plus root omega naught squared. Minus root omega naught squared minus gamma squared. More than we wanted to know. Okay, here we are. Checking the time. Okay. Good. So we've made it a fair distance. I'm just going to discuss our task at hand, and we'll pick it up next time. So we have, if we didn't make a mistake, and we have this minus infinity to plus infinity. And again, let me go ahead and point out that the form of this thing is just some constant times omega minus I alpha divided by omega minus omega 1, omega minus omega 2, omega minus omega 3 times omega minus omega 4. I'll put some nice parentheses here, yeah. Some constant. Okay. And again, this is the way we saw these when we were doing our complex analysis. These were just, z minus z sub 0, z minus this and that. So we take this object into this integral, and of course, we have x hat of omega times e to the I omega t. That's the integral we have to solve. Okay. This is where it gets fun. The complex plane that we are working in is now the omega. Because we're the omega, not dz. So we have to do this integral minus infinity to plus infinity. And of course our strategy is this strategy. We're going to go minus r to r, let r go to infinity. We're going to have 4 roots here. 1, 2, 3, 4. 4 poles, and this time they have physical significance, right? The poles have the physical significance of a driving frequency, a damping term twice here, okay? And here the physical significance, we've got actual frictional damping and the oscillatory frequency in there. So the poles will have physical significance. I think what I'll do is kind of leave it here, because then we'll start out with that next time. I can put another sketch up here. Here's what we'll do. How much time do we have here? Yeah, I'll do one more sketch. Because we're done with this. Yeah. So this formula in blue right here, that times e to the I omega t, that is what we are. Right, this thing here. So we'll end with this, and we will start with the same thing next time to continue discussing it. We just have to do this integral. There's the integrand, x out of omega, e to the I omega t. There's e to the I omega t. So we clearly have 1, 2, 3, 4 poles. And again, I'll go ahead and call this positive driving frequency, negative driving frequency. I'll go ahead and call this the omega naught squared minus gamma squared. And over here minus root omega naught squared minus gamma squared. And then we also have I alpha and I gamma. So these 2 poles are here. These are for the driving force, and these 2 here are from the damped oscillator. We're going to go around and evaluate the integral using the residue theorem for all 4 poles, and when we're done, we're going to send this alpha to 0. We don't have to, we can actually keep it, but we're going to send it to 0 for the damp-driven oscillator. These, because they're complex and they're not going anywhere, are going to be the 2 terms that give us the transient, and these 2 are going to give us the are going to give us what's left, right? the driven oscillation as t goes to infinity. So there's a bunch of physics here. Once you understand what these poles mean, you could evaluate and the other thing is, you have to say to yourself, does this converge, okay, with the e to the I omega t? But we have Jordan's lemma that'll tell us that it converges. So when we finally integrate this thing, okay, we'll go out to minus r. R will have this path there. It's converging integral, and we have the residue theorem to pick off all four of those poles. So we'll start with this next time. We'll put all these pieces up, discuss it again, then talk about evaluating it. And at that point, it's just a lot of bookkeeping because, of course, this doesn't look so bad, but here you have to plug stuff in and make sure you don't make a lot of errors. Okay, good. So we made a pretty good distance. We'll wrap this up next time and maybe a couple more interesting integrals, and that'll probably be it. One more thing. In terms of the homework, of course, the notes as usual, but what you're going to want to do is write out this entire problem from start to finish and really solve it. I'm not going to solve every last step, but take it all the way to completion and then make sure it's all clear to you. So, yeah, homework. This complete problem, which is a good one. It has so many pieces, it'll be nice for you guys to think it over, write it out. Make it all the way to the solution, and then make sure the solution you get here compares to what we got last semester. Good, so that's it for today. See you next time.